a solution contains silver and lead. So we have a solution of that. And then I think we know some concentration, so let's write that down. The concentration of the silver is 1.5 times 10 to the minus 2. The concentration of the lead is 5.0 times 10 to the minus 3. Okay, I'm going to add to this, so I'll go back to the brown pen. To this solution is added another solution. And this is typical fractional precipitation. So I'm adding, in this case, chlorine. The chlorine, we don't know how much, but what I want to know is how much chlorine can I add to cause one of these ions to become a solid and the other one to stay aqueous. So it means like silver, say for example, silver chloride is the solid and lead chloride is aqueous, or vice versa.
How did you know you had to add chlorine?
Because it says in the second sentence, if chloride ion is added to the solution, what concentration, so I'm adding this to the original solution, what concentration of this is required to precipitate each ion? Okay? So they also give us the KSPs, so the KSP for lead chloride is equal to 1.6 times 10 to the minus 5. And the KSP for silver chloride is equal to 1.8 times 10 to the minus 10. Okay, so that's all the information we have. Now what we're going to do, when it's this kind of problem, so we want to know when something starts to precipitate, that's another way of saying it reaches equilibrium. So when it just starts, that's what we call saturated solution. So we're going to not deal with Q in this case. This is only K. So fractional precipitation is K. What will it precipitate is a Q calculation, okay?
Yeah.
So what we did in an earlier problem was a Q. This is a K. So how would that work? Well, you pick one at a time. So it doesn't matter which one you start with. Let's start with this one. Okay. So write out the K expression. KSP equals silver times the chloride ion. Is that okay? What you're going to notice is you have all but one piece of information. So KSP, for example, is 1.8 times 10 to the minus 10. AG, that's given, that's 1.5 times 10 to the minus 2 molar. And we don't know the chloride ion concentration. So that's what we want to solve for, because the question in fact was how much chloride should I add to start precipitation. So Cl minus, in this case, turned out to be 1.2 times 10 to the minus 8. Now it's a molarity, it's a concentration. So in this case, what that means is that that's the concentration of chloride I must add to cause silver chloride to become a solid. Is that okay? If I add anything less than this, say 1.1 times 10 to the minus 8, just a little bit less, it's not going to precipitate. Once I get to that point, exactly, I reach equilibrium, precipitation will begin, and as it gets larger and larger, more will precipitate. Pretty much immediately, everything's going to precipitate. So that's so far is okay. Let's look at the second one now, the lead. So basically, now what I'm doing, I'm going to do the problem all over again, but for the next one. Now again, I want to find the same thing. How much chlorine for this one to precipitate? It's going to be a different number. So in this case, I write the KSP again. Remember, for precipitation, this is 2, because 2 is 2 of them. Okay. So this is 1.6 times 10 to the minus 5. That equals the lead concentration. That's also given 5.0 times 10 to the minus 3 molar. I don't know the chloride ion concentration. Yes?
Why in the ice table you need a Q before the Cl minus, but here you don't need one?
Okay. Little pause on your problem for a second. In the ice table, so a couple things happen. You'll have to square this.
Yeah.
And in the C line of the ice table, if we were doing that, you'd have to put a plus 2x for this term. Because there's two.
Why this case they don't need a Q before?
Why don't I need a 2 here inside? Well, I'm not doing the ice table, first of all.
They are different means, yeah.
Say it again.
And the 2 is different means.
The 2, what it represents is the molarity in the ice table when it's shifting. This is going to be twice that when it's shifting, but there's no shift here. So the C line is 0, there's no shift to the right or left in this case. That's why. So this is, because we're at equilibrium, we're just going straight to it. Okay, resume. Chlorine. Same thing solved, but now you just have to take the square root of it. 5.7 times 10 to the minus 2. Okay? Now what that means, at 5.7 times 10 to the minus 2 molarity, that one's going to precipitate immediately. The second one, okay? So can you see, because this number is bigger than this number, that this one will precipitate first? Is that okay? Did I calculate that right? Yeah, I think so. So that one will precipitate first. So here's what will happen on a kind of a time scale here. If this is 0 molarity of the chlorine, and then I'm adding and adding more chlorine over time. So I'm adding more and more. Okay. In the beginning, they're both aqueous because I haven't added any chlorine yet. Is that okay? So I have, what was it, silver. So as I start to add it, it'll just be aqueous. Both of them. I haven't added enough. Okay. I don't know if I said it backwards earlier. This one's the smaller one. I forgot what I said earlier now. Did I say this one's the smaller one earlier?
Yeah, except the bottom one will precipitate.
Oh, backwards. This will be first, sorry, and this will be second.
How do you know?
Because I need to add, this adds the least amount of chlorine. I think I got it mixed up in my brain a little bit. Yeah, undo that last part. I don't know if I'll be able to edit it out, but this is the smaller number, so I add less chlorine to cause this to precipitate first. I have to add more to get this one to precipitate, because this is the bigger number.
Yes.
Okay, did that make sense? Okay, so once I get to 1.2 times 10 to the 8th, that's the smaller number. Later, I will get to 5.7 times 10 to the minus 2 molar. Okay, so this is the bigger number. I'm coming to it later. Okay, after I pass this, the first one becomes a solid, and that's the silver. The lead is still aqueous because the lead hasn't reached its number of 5.7. Is that kind of okay? Now we're adding more and more. We're waiting for the lead to precipitate. It finally gets to this number, which is the equilibrium value for lead. And now they're both going to be solids. Or precipitates. Is that kind of okay?
Yes.
Okay, so if you, couple things about this. If you wanted to separate these, you'd have to pick a concentration between these two numbers. One would be a solid, one would be a liquid. You would just pour the liquid out, and the solid, you'd have just thus separated the two. Another couple things. So what do? When you fractional precipitation, there's going to be one of them that have an unknown concentration, and that's what you're finding. You do two separate cases, you use K for both, you do all the same math, and you solve for that unknown concentration. The smaller one is the one that has to precipitate first because you're adding less. You don't have to add as much. And once you add more and more chlorine, then finally the second one will precipitate. Usually what's going to happen is the one with the smaller K, you see the top one has a smaller K, that's going to usually precipitate first, typically. The one with the bigger K, it slightly more favors the right-hand side. So because of that, it's going to precipitate usually second. So some people, if it was like what's first or second, like one we did a little earlier, you don't even need math at all. Yeah, you can just look at the number. But you have to be careful because you got the square root thing and you don't know what that's going to do. So it's always safest to calculate it. And then now, this is what happens. The first one precipitates, then the second. Is that okay? So no ice tables whatsoever in fractional precipitation. Unless, yeah, I can't even think of a question off the top of my head that would need it.